The day we have Alex Postnikov, who will tell us about open problems in combinatorics.
Can you hear me now? Okay. So thank you very much for to the organizers of this conference for the invitation. So my purpose today to give a little bit different talk than other speakers, because I'm not going to cover one particular area of combinatorics. So basically, I'm going to just present you some selection of problems, which are actually pretty random problems. And I'm not claiming that these are the most important or even important problems. And there are some of them are related to each other, some are not really related. So the only criterion that I was using is that I am trying to present a problem that I can present in 5 minutes. So, and I'll see if I'll have enough time for all of them, but there will be pretty short problems. Okay, so the problem number one is related to Schubert calculus. And more specifically, so a while ago, together with Sergei Fomin and Sergei Gelfand, we wrote a paper about quantum Schubert polynomials. So quantum Schubert polynomials. So they're denoted by like this. They depend on a permutation, W. There's like a little letter Q. And they're polynomials in with integer coefficients in x1 up to xn, q1 dot qn. And they generalize or specialize to the usual Schubert polynomials. So by the way, I want to ask you, is there anybody in this audience, except Vic Reiner, who does not know what Schubert polynomials are? Okay, so there are a few people. So since I said I'll be short, I'm not going to define Schubert polynomials. So problem number one is not an open problem, but if you don't know what they are, so you can find the definition. But so these are some interesting polynomials that generalize Schur polynomials. So like in special cases, they are equal to Schur polynomials. And in general, these usual Schubert polynomials are related to intersection numbers of Schubert varieties. So there are some polynomials used to, kind of important from geometrical point of view. They allow you to count intersection numbers of Schubert varieties. In the same way, our quantum Schubert polynomials allow you to count more general invariants, which are called Gromov-Witten invariants of Schubert varieties. Again, I'm not going to, since I said I'll be short, I'm not going to explain all these words, but you can like check the paper for all definitions. But problem number one is to give a combinatorial rule for quantum Schubert polynomials. So in our paper, we give a recipe to calculate these polynomials. And this recipe, I would say it's not entirely combinatorial. It's pretty much combinatorial, but we use a little bit of linear algebra. So, so how we use linear algebra? Let me explain. So what we did, so first you start with the usual Schubert polynomial, classical, not quantum Schubert, without letter Q here. And you want to expand this usual Schubert polynomial in a different basis, which we used, which we call the standard elementary monomials. So let me denote it by E sub A. So A here is just a vector, A1, A2, and so on. And E sub A is just elementary symmetric polynomial sub A1 in x1. Then you have another elementary symmetric polynomial in x1, x2, and so on. So they're products of elementary symmetric polynomials in different numbers of variables, in one variable, in first two variables, in first three variables, and so on. So one can show that these polynomials form the same basis in the same space where like Schubert polynomials live, and we want to expand in this basis with some coefficients. Let me call them C sub WA, E sub A. And that's the first step of our recipe. And second step of our recipe is pretty simple. There's like a pretty explicit way how to quantize these standard elementary monomials. There's like some way, pretty simple way to embed Q variables in them. So, but question is, what can they say about this? Can we actually find a rule for these coefficients? So just expand usual Schubert polynomial in terms of these other bases. Okay. In a different paper, written together with Richard Stanley, the paper called Chains in the Breuer order, we studied other polynomials, so which we called degree polynomials. So let me denote by D sub W. They're also labeled by permutations, and now they're just polynomials in just variables x1 dot xn. There are no any q's in them. And so these polynomials, their values at particular point gives the degree of Schubert variety. So again, they're important from geometrical point of view. And probably, and they have another name for there is another name for this polynomial. We can also call them dual Schubert polynomials, because these polynomials form a dual basis to the basis of Schubert polynomials with respect to the following pairing on the polynomial ring. So form the dual basis to the basis of usual Schubert polynomials, okay, with respect to the following pairing. So you take one polynomial f and another polynomial g in x's. So then you plug in partial derivatives instead of x's. You take f of partial over partial x1, partial over partial x2, and so on. Apply this differential operator to g of x1, x2, and so on. And then calculate the constant term. So specialize after this, specialize all x's, x1, x2, and so on to 0. So that's a pairing on the polynomial ring. And actually it's a little bit, so I'm skipping some details, but actually it's a little bit nicer to consider these polynomials in infinitely many variables. And actually instead of permutations, in ascent talk about permutations in ascent infinity. Anyway, so with respect to this pairing, there is a dual basis. We get these other polynomials. And of course they're polynomials. They can be written as linear combinations over all monomials, like let me call it C tilde of W A, x to the A. So x to the A like x1 to A1, x2 to A2. Problem number 2, give a combinatorial rule for this expansion. Okay, so expand these dual Schubert polynomials, or degree Schubert polynomials in terms of monomials. Of course, many of you know very well how to expand usual Schubert polynomials. So usual Schubert polynomials can be written as a sum over all monomials. And let me denote these coefficients k sub W A, x to the A. So I'm calling these numbers Schubert-Koska numbers. And the reason is that in cases this is a Schur polynomial, then the coefficients in front of monomials are the usual Koska numbers. So these are some generalizations of well-known Koska numbers. They're called Schubert-Koska numbers. And actually, I'm sure many of you know there are very nice combinatorial rules for these numbers. For example, in terms of RC matrices, or pipe dreams, or bumpless pipe dreams, and so on. So there are like different variations. So there is a combinatorial rule for these polynomials. So these are known. So number of pipe dreams. Now let's kind of do the opposite thing, expand a monomial as a linear combination over permutations, W of, let me denote this kind of inverse, so some coefficients, a W of Schubert polynomials. So you want to write a monomial as a linear combination of Schubert polynomial. And of course, this is just, so here we have n factorial by n factorial matrix. We just need to take the matrix inverse of this matrix. So question, what are these numbers? Okay, so here we have 3 different problems, but actually I claim that these are not 3 different problems, but it's the same problem. So these coefficients up to some kind of reordering are the same thing as these coefficients and are the same things as these coefficients. So these 3 problems are equivalent to each other. And the question is how to find a rule for them. So in the paper with Stanley, we actually give a rule kind of known. So these inverse entries of these inverse Schubert-Koska numbers are known. We give a rule for free one-to avoiding permutations. And in this case, actually, all these numbers are always 0, 1, or -1. So by the way, I should mention that these numbers are not necessarily positive. They can be either positive or negative, and the combinatorial rule means that I actually give a rule for this sign. So we want to kind of give a subtraction-free formula. It tells you what the sign is and what's the absolute value of these numbers. So this is for free to one avoiding permutation. No, it's also not too hard. So we didn't write it explicitly, but it's possible. We kind of make a remark how to do it for the auxiliary permutations. So for the auxiliary permutations, again, we use this fact that Schubert polynomials in this case are known as flagged Schur polynomials. So it's you can also do it for actually not kind of upside down the auxiliary permutations, which are for free one to avoiding, free for one to avoiding. So this is like a free for one to avoiding permutation. Okay, but it would be nice to give a general rule. Okay, that's kind of problem number 1 or number 1, 2, 3. Okay, so so by the way, I kind of like in the classification of Sergei Fominov problems. So he says some problems are kind of open and some problems are widely open. So basically, widely open problem means that many people try to solve it and they gave up any hope to solve them. So I hope that at least some of the problems that I'm going to mention are not widely open. I'm not sure about this problem, if this problem is widely open or not, but at least in some cases, maybe in general case, one can try to find these numbers. Okay, so let me move on. So the next topic is Schur positivity. No, oh yeah, no, you can interrupt me at any point. Actually, sorry, I'm kind of said I'll use 5 minutes for a problem. Now I'm using more than 5 problems, but anyway. So yeah, so questions? Okay. So Schur positivity. Okay, because many of you heard about you give some symmetric function and you ask whether it can be written as a positive linear combination of Schur functions. So more specifically, there is like more particular type of Schur positivity questions. Then you take product of 2 Schur functions, S nu, S delta, minus S lambda times S mu, and you ask whether this difference is Schur positive. So this notation greater than or equal sub S means that it's a linear combination, positive linear combination of Schur functions. Oh, maybe I should write it like this, whether it's Schur positive. Okay. More specifically, so together with Thomas Lam and Pasha Pilavsky, again, a while ago, we've proved the theorem. Where we prove the following result: S lambda plus mu over 2 times S lambda plus mu over 2 minus S lambda minus times S mu is Schur positive. Okay, so let me tell you what that means. So lambda and mu are two partitions, and we are going to fix the number of parts. We are going to require all of them have exactly n parts. Now you add them just part by part, like as vectors, and divide all parts by 2. Okay, so that's what lambda plus mu over 2 means. Of course, this number may happen to be not integer, but half integer. So to solve this, but Schur functions are defined for integer partitions. So what do? We are going to put floor and ceiling. So you round these numbers either from below or from above. Like in one case, like just part by part. And turns out that this expression is Schur positive. And in particular, that implies some earlier conjectures on Schur positivity due to Postnikov and Fomin, Fulton, Lee, Poon. Okay, so basically, but this conjecture says, so this property we kind of called Schur log concavity property. So here you think about Schur functions not as functions of x. Usually people think of them as functions of x's, but here we kind of think of them as functions of partition. So, and as a function of partition, it kind of has a log concavity problem. So so you have lambda, you have mu, and you kind of jump to the middle of the line segment between lambda and mu. So lambda plus mu over 2, and it turns out that the square at this point is greater than or equal to s lambda times s mu. That's like log concave function. Okay. But we also, at that time, we also had so this seems to be actually like a tip of an iceberg. So that's some nice property, but it turns out that it seems to be true that, so we don't need to kind of jump all the way to the middle of this line segment, but we kind of maybe slightly change lambda and slightly change mu, kind of approach. So we kind of go between lambda and mu, go kind of approach, kind of start moving in this direction. They also seem to be Schur positive. And we formulated a conjecture. Well, we didn't put it in the paper, but I think it's kind of we kind of mentioned in some other places. So conjecture says the following, that this expression S nu times S delta minus S lambda times S mu is Schur positive if the following is true. So first of all, lambda plus mu equals to nu plus delta. That means that kind of then you start moving from lambda towards mu. You should also start moving from mu towards lambda by kind of the same vector. And nu and delta belong to certain parallelepiped pi defined by lambda and mu. And I'm going to tell you what this parallelepiped is. Okay, so let me draw the picture. So this is question to you. Does anybody know what I'm drawing here? So that's the Coxeter arrangement. So like, or Bray arrangement. So the hyperplanes are xi's are equal to xj. That's the case n equals 3. Okay, and lambda and mu are partitions. They kind of dominant weights. So they belong to this fundamental chamber. So maybe both of them are in the same region called fundamental Weil chamber. And what we need, so what happens is that we can find some, and these other regions are called Weil chambers. We can find one Weil chamber so that if you translate vertex of this Weil chamber to lambda, then it contains mu. So there's like a translation of a Weil chamber like this. So let me move mu here a little bit. And similarly, if you take the opposite Weil chamber and translate it to mu, you get the other Weil chamber. An intersection of these two opposite shifted Weil chambers is this what we call this parallelepiped pi lambda mu. And if points nu and delta happen to be inside of this parallelepiped, we kind of conjecture that it should be Schur positive. Now, there is some evidence for this, so it has been not hard to check for n equals less than or equal to 3. Also, at that time, Pasha Pilarsky, who was a graduate student, it was like a while ago, I think more than 15 years ago, was a graduate student. He had a like Europe project with Galina Dobrovolsky, who was an undergraduate student. And in particular, what they proved, they proved a weaker version of this result, which they called the containment positivity. So, or content positivity, meaning that if there is some Schur function that appears in this product, then it should also appear in this product with non-zero coefficients. It means that there is some evidence for this. And also Pasha told me yesterday that maybe David Spire or his student thought about this. I don't know if David is here, but okay, so maybe there are some other results. Okay, so anyway, so there are some results or partial results which are known. Okay, so, oh, do you know the answer to this conjecture? Okay, sure. Yeah, I mean, so I didn't quite get the question, but we want to, yeah, right. Oh, yeah. So these both partitions, so in our picture, let me write the picture, I hope it will answer. So you have this parallelepiped, like this. Before this is lambda mu, and we want nu and delta to be inside of this parallelepiped and kind of centrally symmetric to each other with respect to the midpoint of this parallelepiped. So in this case, we have conjecture there should be Schur positivity property.
So just let's pretend that you would be everywhere except on 1 and 3. Or sorry, let's grant that you agree with nu and delta except on like one row.
Okay.
They just sort of circulate in that
Probably
row.
yes. So, but I need to think about this because I'm a little bit overloaded with math today. There are too many talks, so I'm trying to be, anyway. So let me think about this, but probably something like this is true. But anyway, so that's the concrete conjecture. Okay, now, as I said, I hope that this is not a widely open problem, and there is some possible approach to this. Maybe let me suggest one possible approach. Yes. Maybe yes. Maybe, but let me mention one kind of possible ways to approach this problem that I have in mind is to use honeycombs. So what are the honeycombs? So maybe the story probably starts with Berenstein and Zelevinsky, who introduced certain things which are called some combinatorial reformulation of the rule for Littlewood-Richardson coefficients. So maybe I should tell you what Littlewood-Richardson coefficient is. You multiply two Schur functions, expand them in the basis of Schur functions, and these coefficients, called Littlewood-Richardson coefficients. Okay, and there is a famous Littlewood-Richardson rule, and Berenstein-Zelevinsky found a kind of rule, kind of symmetric way to formulate Littlewood-Richardson rule in terms of what they call, well, they call them triangles. Now it's things called Berenstein-Zelevinsky triangles. Then Knudsen and Tau give a nice graphical reformulation of Berenstein-Zelevinsky triangles, which are called honeycombs, and they use it to prove saturation and other nice things. So let me tell you what these Knudsen-Tau honeycombs are. So let me draw, you need to draw a honeycomb. Okay, so I'm drawing here regular hexagons, but they are not necessarily regular, but kind of a bunch of hexagons. Okay, so okay, so that's a honeycomb for n equals 4, and again, here I think so all directions of these kind of lines are fixed, but they're not necessarily kind of regular like this. So some sides can be shorter, some are longer, but these positions of this rays are fixed, these boundary rays, and they are given by parts of the partition. So this is lambda 1, dot, 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 up to lambda n. Here mu1, mu2, up to mu n. And here, well, the third partition is kappa 1, kappa 2, up to kappa n. So we kind of fix these boundary rays, and you look at all possible kind of ways to draw pictures like this. and you can formulate it as certain by a bunch of linear conditions. So in fact, this is certain polytope. So this kind of polyhedral way to think about, and the number of lattice points inside of these polytopes, the number of integer. So number of pictures like this are all lengths of all little intervals here are integers, which are greater or equal to 0, is exactly the number of little Richardson coefficients. So C lambda mu kappa equals number of integer honeycombs. Okay, now how does this kind of way to think about little Richardson coefficient help us? So here, so what we want to see is that whenever you have some things that appear in the expansion here, this some little Richardson coefficients, there is another little Richardson coefficient here, and we want to see that this other little Richardson coefficient is greater than or equal, then kind of all little Richardson coefficients in this expansion should be less than or equal than little Richardson coefficient in this expansion. In other words, we want to fix kappa can be arbitrary, but kind of fixed. So you fix this position of this race, and you start moving this boundary race for lambda and mu, and you want to move it in such a way such that the number of lattice points increase. Okay, but there is also this condition. So lambda plus mu should say, for example, lambda 1 plus mu 1 should be equal to nu 1 plus delta 1, and so on. That means that this race for lambdas and nu are kind of paired with each other. That means that if you move lambda 1 by some amount, say clockwise, then you should also move mu 1. If you add something to lambda, then you should subtract something from mu. So if you move lambda 1, shift it here, then you should move mu 1 by the same amount, and so on. So you want to kind of move them in such a way such that the Richardson coefficient increases. Okay, but there is nothing that should force us to kind of match lambdas and mu's in this particular way. We could try to match them by some other permutation. So what we could try to kind of explore through positivity of expression, something like this: S lambda plus some vector A times S mu plus some permutation of this vector W of A minus S lambda S mu. We can try to kind of explore this kind of through positivity. So where W is some permutation, some fixed permutation. So for example, and like our original conjecture is about the case where this W is identity, but we can try to take some other permutation. For example, the longest permutation, W equals to W naught. Namely, now we want to identify lambda 1 with mu n and lambda n with mu 1. So we want to kind of move these two rays simultaneously and these two rays simultaneously. And it turns out that this question is much easier. So here we have a very nice and complete answer. And the reason is that what we can do, we can just literally move these two rays up by increasing length of this line segment. By kind of increasing length of all vertical line segments, we could embed Bernstein-Zelinsky polytope for this, for lambda and mu inside Bernstein-Zelinsky polytope for these two guys. So here's the theorem, which is kind of pretty easy. Theorem is that if A1 is greater or equal to A2 is greater or equal to greater or equal to AN, then we actually do have this true positivity. So then, I don't want to write it, but then we have this true positivity. Yes, for W equals to W naught, yes? Yeah, thank you. Maybe, well, so there is a, well, I don't know. There's any chance for anything, I don't know, but, well, I don't know actually if we explore it, but that's a good question. So, yeah, so some other conjecture, questions, yes? Okay, very good question. Another open question. So, so question: what what can they say about if it's true positive, what can they say about the differences? And I think, well, yeah, I don't know, but this is definitely a nice question. And yeah, it would be very nice to try to understand this. But again, for the longest permutation, actually, the answer is easy. And we want to kind of start with the longest permutation and kind of try to decrease its length, maybe by, so what, and in this case, for longest permutation, we can literally embed one Bernstein-Zielinski polytope inside of the other. In general, I don't expect that you can literally, and it's not true that you can literally embed one polytope inside of the other. But what we hope is actually there should be some piecewise linear transformation of the polytope for lambda and mu. So you have to kind of cut it into pieces and glue them in a different way, recombine them, get another polytope which is embeddable in the inside of the other polytope, so that you can prove that these numbers increase. And the way to approach this is actually, well, I hope to use combinatorics of Plebbe graphs. By the way, kind of there initially I kind of started to study Plebbe graphs by actually looking at, you know, honeycombs and these kind of pictures, so you can kind of relate it to some nice graphs that I think appeared in some talks before, and doing some kind of cluster transformations and so on. So hopefully kind of cluster algebra techniques can help you to do this kind of piecewise linear transformation and kind of solve this question in general. That's kind of my hope, but I don't know. Yes? Definitely. And again, in the limit, these little ratios and coefficients become Koska coefficients. That's another, yeah, would be nice to kind of see what happens to Koska numbers. Okay, in other words, yeah. Yeah, but what was your question? Okay, so I think we looked at, the question is, have we looked at Koska analog? So I think we looked at some cases, and there are a lot of, you know, special cases. I'm not ready to kind of formulate exact theorem right now, but that's definitely, and many things become simpler. I think there's like, for Koska numbers, there is probably theorem of this kind, but okay, let me move on, because I promised you to use only 5 minutes for a problem, and now I use more than half of my time only on the first two problems, and I wanted to give more than two problems. So another topic or kind of twist of Schur positivity appears in our work with Miriam Farber on arrangements of equal minors. Okay. Arrangement of equal minors. Okay, so what the arrangements of equal minors? So suppose that you have some matrix, K by N matrix, and I is going to be a subset of columns. So I is a K element subset of numbers from 1 up to N. So subset of columns. And then you can take the corresponding, you know, submatrix, square K by K submatrix, calculate its determinant, and these determinants are called maximal minors. Okay, now, as you probably know, Schur polynomials, defined like classical definition of Schur polynomial, is a quotient of two determinants, one determinant divided by the other determinant. The bottom is just usual Vandermonde, and the top is kind of also now like Vandermonde-like determinant. So it means that we want to, instead of studying Schur polynomials, we can study these determinants, these minors. Well, for some particular, so they become Schur polynomials or rescalar Schur polynomials for this particular matrix, kind of that looks like a Vandermonde matrix. But I want to maybe try to understand these questions just for arbitrary matrices. And as you So what we're going to assume that all these minors are strictly positive. So because all van der Monte determinants like are strictly positive. So I'm going to assume that all these maximum minors are strictly positive. It means that if we're actually talking about positive Grassmannian, but I don't want to define it right now. And these minors are not algebraically independent. There are some relations between them known as Plucker relations. So for example, kind of the prototypical example of Plucker relations for k equals 2 and n equals 4 is that delta 1, 3 times delta 2, 4 equals to delta 1, 2 times delta 3, 4 plus delta 1, 4 times delta 2, 3. Okay, so I like to draw this relation by kind of arranging points 1, 2, 3 on a circle, 1, 2, 3, 4. And I'm going to represent minor by drawing a diagonal, like delta 1, 3 becomes this diagonal between 1 and 3. So here we have a pair of crossing diagonals. And here there are two ways to uncross these diagonals. Well, actually, I think, yeah, like this, 1, 2, 3, 4, plus 1, 2, 3, 4. Okay. Now, just look at this relation, we can get some Schur positivity results. For example, two Schur polynomials. Well, I mean, if you divide all these terms by van der Monte, you get Schur polynomials. So these two Schur polynomials minus these Schur polynomials equals to product of these Schur polynomials. So it's Schur positive. So you can get some Schur polynomials, Schur positivity by looking at at these from Plucker relations. Now, in our paper with Miriam Farber, we asked kind of slightly different but related question is, what can we say? Can we actually, what are possible equalities and inequalities among all these among all these minors? So for example, can we set some subset of minors? Can we require that all of them are equal and all other minors are strictly greater than this? Okay, and we call such things as smaller arrangements of smallest minors. Or another option is, can we set some sort of subset of minors equal to each other and require that all other minors are strictly less than this particular subset? So this calls these things arrangements of largest minors. So we talked about these arrangements of smallest minors and arrangements of largest minors. And so how to draw an arrangement just by, in this case, how to kind of, what can we do? So for example, we can do the following thing. So we can make these two things equal to each other. And also this, we can make all these four minors equal to each other. And one of them, and say maybe delta 1, 3 is also equal to these same things, but this guy will be strictly larger. So it means that there's one particular arrangement of smallest minors where we can, all minors corresponding to all edges in these diagrams are equal, and also say one of these edges are equal. And that is an arrangement of smallest minors, kind of, in this case. And the missing diagonal is going to be strictly larger. So another option, like, so if we want to describe arrangement of largest minors, but we can actually make these two guys equal to each other, and maybe, well, let me actually draw you another arrangement of largest minor. Well, arrangement of largest minors. What we can do, for example, we can make these two things equal to each other, and maybe these also, and these are equal. So delta 1, 3 equals to delta 2, 4 equals to delta 1, 2 equals to delta 3, 4, and these two guys, two missing guys, will be strictly smaller. So this is kind of smallest minors, and these are largest minors, or arrangement of largest minors. Okay, and as you see from this picture, then we're talking about smallest minors. So these things are kind of trying to be kind of non-crossing. So all these, things don't cross each other. On the other hand, when we are talking about largest minors, all these kind of these diagonals are trying to cross each other. So, and kind of intuition in general, this should be, that's like case where k equals 2. Intuition that in general, these things, kind of smallest minor should correspond to something which is not crossing, and largest minor should correspond to something which are like very highly crossing. Now, how to define these things in general? In general, we can define them as follows. So first, let me define the notion of things which are kind of highly crossing. So you have two subsets, I and J, two k element subsets, I1 less than I2, dot less than IK, and J1 less than J2 less than JK, two k element subsets, and we say they are sorted if I1 is less than or equal than I2 is less than or sorry, I1 is less than or equal to J1 is less than or equal than I2 is less than or equal to J2, and so on. So basically, if you ignore like common entries, they should kind of interlace. Kind of, they are kind of as interlaced as possible. So in this case, we are saying they are sorted. On the other hand, we say that they are weakly separated if, let me draw a picture. So if you take set theoretic difference I minus J and J minus I, so basically throw away all common entries of these subsets and arrange the entries on the circle, then we can actually find diagonal that separates one set from the other. So these are kind of things, kind of analog of things for K-element subset of like the most kind of non-crossing things. So these are weakly separated are kind of the most non-crossing things, and sorted are kind of the most crossing things. Okay, now since I don't have much time, so let me formulate result, which we proved with Miriam. So one theorem is that these two notions are, okay. So theorem is, if you have a collection of, so by the way, collection means a set of subsets. So collection just, I don't want to say like set of subsets, I'll say collection of subsets. So C is a collection of K element subsets. So some subset of n choose K. And so it is an arrangement of largest minors. In other words, we can make all minors corresponding to these subsets equal to each other and all other minors strictly less than them, if and only if it is C is sorted, like pairwise sorted, like any two elements, any two I and J in C are kind of interlaced as much as possible. Also, we say that another result that we proved that this collection, so if C, again, this kind of collection is weakly separated, then it is an arrangement of smallest minors. In other words, if we have a collection of subsets such that any two of them are kind of as separated as possible, then you can actually make all these minors equal to each other and all other minors strictly larger than this. Notice that in this case, I didn't write it, but in the first theorem, we have if and only if. These two conditions are, for largest minors, these two conditions are completely equivalent to each other. In this theorem, we have only one direction. In this theorem, we have only one direction, namely weakly separated, implies that it's an arrangement of smallest minors. And actually, the opposite is not true. We found some counter examples then of collections which are not weakly separated, but they can be made into like they correspond to smallest minors. So open problem is to actually characterize collections, all possible collections of smallest minors. So how to, and we have a conjecture that if you in addition require that this subset has the maximal possible cardinality. So conjecture in the last, so we have if and only if C has the maximum possible cardinality, there is actually explicit number for the maximum possible cardinality. If cardinality of the C is K times n minus K plus 1, that's one can show that that's maximum possible cardinality of a weakly separated collection. So in this case, actually, we conjectured that arrangement of smallest minors is equivalent to weakly separated, but not in general. Now, some maybe comments are so sorted collections earlier appeared in a work, like in my work with Thomas Lyman, some polytopes, and also in earlier work of Bernd Sturmfels on Grobner basis. So these things are not just kind of some random things, but they're related, and they have very nice and beautiful structure. So again, you can find the details in the paper. Weakly separated also is very important notion. It first appeared in the work of Leclerc-Zelevinsky, and later it was like one of the motivating examples for introduction of cluster algebras and things like this. So it's related to cluster algebra, related to Plaber graphs. So maximal weakly separated collections are in bijection with Plaber graphs that appeared in some talks before. So this kind of also important notion, but kind of these theorems suggest, I mean, these kind of counter examples already have suggested that kind of theory of cluster algebra helps, but there are some things beyond cluster algebras. So basically kind of my wish is to kind of, can we actually extend? So there are like some indications that there might be some more general objects than, clusters. Again, it's not like well-posed question, but is it possible to kind of extend the theory of cluster algebras and mutations and things like this that would cover, kind of help us to answer these questions? Okay, yes.
Is it easy to give an example of a smallest minor that would not be weakly separated?
Okay, so we have in the paper, I don't have it offhand in the paper, there is example, and it's not easy. Like it required actually, and it's based also used on some, pretty tricky manipulations with Plaber graphs. So, but in the paper, we give a concrete example, and it's kind of pretty large picture. Like, so basically, example is given by a large picture that takes the whole page. But anyway, so if you're interested, you can find it in the paper. Okay, but let me move on to another problem. I think I have probably enough time to formulate one more problem. Okay, so next problem is, let me call it PRV vectors. Oh, actually, I want to formulate two more problems. I have, how much time do I have? There are like 3 problems that I left. Actually, let me formulate a shorter problem first, and if I'll have time, I'll talk about PRV vectors. So, short problem, let me move back to Schubert calculus, because that's kind of, so, and of course, I'm not going to talk about like problems that many of you thought about. Schur, what is Schur times Schur? Okay, but hopefully, slightly easier problem is what is, no, not, sorry. many think of Schur potential everybody knows, but what is Schubert times Schubert? So how to multiply two Schubert polynomials? Okay, so that's kind of interesting problem. But what I'm going to hopefully slightly easier problem. What is a Schubert times monomial? Okay, so we have a Schubert polynomial, and you multiply it by monomial, and you want to expand it in the basis of, I know these some coefficients, you know, W, A, U in the basis of Schubert polynomials. What can we say about these coefficients? And several years ago, Alan Knudsen asked me this question. So he said, and in particular, he asked me this question, if this is a square-free monomial. And I kind of started to think a little bit about this problem, and I noticed some interesting patterns if this monomial is square-free. But then I actually realized that this question has already been answered in my paper that I wrote when I was a graduate student. It's called on a quantum version of Pierre formula. So anyway, formula that I proved in that paper actually in special case implies the answer to this question, known if x to the a is square-free. There is like a explicit way. And in this case, the coefficient, in particular, these coefficients are equal to plus or minus 1 or 0. So like multiplicity-free formula. Again, they can be negative. There is explicit rule for sign and so on. But if x is not square-free, it involves, you know, higher order terms. Then actually there can be some multiplicities. But question, can we actually find an explicit rule for that? Like, is there an explicit way to describe the sign of these numbers and the absolute value? Okay, so that's question. And let me mention another open problem. I think they have 5. Okay, so first of all, as you mentioned, Monk formula implies this rule, right? Because Monk formula gives you a way to multiply by xi. So it means that if you know how to multiply by one variable, you can know how to multiply by any monomial. But it turns out if you apply Monk's rule, you get some function experiment which is redundant. There are going to be a lot of cancellations.
But this one was square-free.
No, Monk's rule, like if you apply Monk's formula, and again, this is not just any collection of xi's. So there will be some cancellations. Like if you apply Monk's rule, there will be a lot of terms. And it turns out that all of them cancel and only at most one stays, you know, anyway, so it's Monk's rule doesn't imply square-free property, but there is a what I call quantum Pierre formula that implies that it's square-free. Okay. Okay, but right, I mean, in principle, everything follows from Monk's formula, because if you know how to multiply by xi, no. Well, I mean, maybe in final it's based on the Monk's formula, but I mean, anyway, so it's related to Monk's formula, but I'm saying it's not like immediately clear from Monk's formula that it will be multiplicity free. Okay, so I think let me formulate one more problem. So problem about PRV vectors. Do I have enough time? Oh, I have enough now. So PRV vector, PRV. Oh, no, PRV. Okay, so there is some result in representation theory which is called PRV conjecture, but actually it's not a conjecture. It was proved more than 30 years ago by Kumar and Mathieu. It's called. So this result says that if we're in some semi-simple Lie algebra, take tensor product of two irreducible representations of semi-simple Lie algebra and expand it, like write it, you know, in terms of, you know, irreducible representations. Here you get these little, well, generalized little Richardson coefficients in type A. They are exactly the same thing as these little Richardson coefficients. So theorem or PRV conjecture says that these little Richardson coefficients C lambda nu is not zero if nu is sum of two permutations of lambda and mu. So if this nu is a dominant weight and it happened to be W of lambda plus U of mu, so for two Weil group elements, then the coefficient is not zero. Again, this has been proved, and there are a lot of generalizations of this result. That's kind of an old classical result. And in type A, this theorem has a very nice and short proof using honeycombs, because in type A, these coefficients are given by honeycombs. So you just need to show that there exists a honeycomb in this case. And let me actually draw this honeycomb. I just like prove by single picture for in type A. So basically, we need to just draw one particular honeycomb of this particular type, which I like to call Y arrangement, and some people can call it tropical line arrangement. So that's like one particular honeycomb. So say if this is lambda I, this is mu j, and this is going to be lambda I plus mu j. So basically, you kind of take any matching between lambda and mu, and that's exactly what like this, what you get on this side is exactly this some permutation of lambda plus some permutation of mu, like just kind of add the permutation terms twice. So that's the proof basically. Type A follows directly from honeycomb model.
One for all three on the same block.
Oh yeah. It has, oh sorry, I am supposed yeah. Anyway, so that's sorry, they're supposed to be on the same line as David. Anyway, so that's the proof of PRV conjecture in type A. But we can ask question, what are like, let's even specialize this to something like the easiest case that you can imagine, or maybe not the easiest, but now assume that lambda equals to mu equals to what is called the rho, which is just n minus 1, just this staircase partition. So in other words, what we're doing is, so question is, what are possible PRV weights? Like what are possible weights that appear in this formula? So in other words, you take any permutation, two permutations, U and W, permutations of numbers from 1 up to n, and think about these permutations as vectors, and add these vectors, U plus W. So then you get vector V. We call this PRV vector. Question, can we actually describe all possible PRV vectors? So somebody gives you a vector of length n. Question is, can you actually write it as sum of two permutations? Looks like totally trivial things to do, but actually it's not as, if you try to do it, it's not kind of totally obvious. If require, so how can we describe all possible sums of two permutations? So now let me tell you some conditions on PRV vectors. Of course, I'm drawing Coxeter or Bray arrangement again. So of course, if you take kind of all permutations and represent them by points, you get this polytope. So that's a question to you. Does anybody know the name of this polytope? Oh, it's hexagon. Yeah, very good. It's a hexagon. And in general, more general, it's a more not just it's like a regular hexagon, most regular, most symmetric kind of hexagon. It's called a permutahedron. Let me call it pi n, or just pi. Now, if you add two permutations together, that means that you just take Minkowski sum of two permutahedra. So you get like twice the like dilated permutahedron. So you get, so this PRV vector should belong to, dilated. You dilate it by a factor of 2. Or like, it's like 2 pi. And in particular, PRV vector should belong to this dilated permutahedron, well, intersected with the integer lattice. Okay, we can ask, is it like, maybe this is just the set of all lattice points in this dilated permutahedron. And we check, and it's true for n equals 1, true for n equals 2, it's true for n equals 3, 4, 5. But for n equals 6, we find a counterexample. Find a hole in this dilated permutahedron, which cannot be written as a sum of two permutations. And the first hole, let me tell you, write down the first hole. That's kind of exercise for you if you have nothing else to do today, to check that this vector, it kind of first know how to see it belongs to this twice dilated permutation, but it cannot be written as a sum of two permutations. That's the first hole. And for large n, you have more and more holes. Okay, so question is, can we actually but what you notice that in all examples of these vectors inside of this dilated permutation, which are not paired vectors, they will be highly degenerate. Like you see in this example, there are a lot of equal coordinates. So we wrote a paper with Berbecois, Mansour, and Severini, which is called X-rays of permutations, where we made a conjecture which is equivalent to the following, that all holes actually appear like on these hyperplanes, xi equals xj. Like for any hole, like so basically all holes will be all non-pair V vectors inside of these twice permutation should be very degenerate. So, but if you kind of move away from these hyperplanes, then actually all other lattice points can be written as. So I'm not sure if it's true or not. Maybe we didn't search hard enough for counterexamples, because I'm kind of. But it would be very interesting to either to try to prove or to disprove this conjecture, because it's kind of equivalent to some other interesting things, and it's also related to things which we call X-rays of permutations, kind of describing X-rays of permutations. And I think I used up my time, so let me stop now.
Thank you very much, Alex. Are there questions? Yeah, nice and loud, please.
Yeah. Yeah. Mm-hmm. Uh-huh. Oh, okay. So yeah, maybe so there's you're saying there's some interpolation between these EK. Mm-hmm. Mm-hmm. Okay. Yeah. So. Okay. So yeah, I guess that's a kind of good approach, and yeah. Yes.
So if you're talking about the Lamb-Boyarsky Postnikov conjecture, you have the partial relation on pairs when mu delta mu, where you expect there to be inequality.
Mm-hmm.
What are the offset edges of that relation? What are the minimal ones?
So what are, sorry, what are the minimal?
What are the minimal errors of pairs?
Oh, in this partial order.
Yeah.
Good question. I don't know the answer offhand. So the so David asked the following question: is that moving back to this Schur positivity question? So where S lambda S mu is less than S nu S delta. So if we have this conjecture, there is a partial order between pairs of partitions. So in this, if it satisfies this condition, we say lambda pair lambda mu is less than pair of nu delta. David asked, is what are the minimal elements of this partial order? And I think that's an interesting question. I don't know the answer right away, but hopefully, or maybe you know the answer, or, but it looks like the answer is not why, I mean, hopefully it is solvable. Yeah, yeah, that's definitely a good question. And I think maybe we'll thought about these questions with Pasha and Thomas. I don't know the answer right away, but yeah, that's definitely kind of important and interesting question. Yeah.
All right. If there are no more questions